Hi, everyone. I'm Debbie with Nixene Publishing, and I'm here with Adrian Nixon, our editor-in-chief of the Nixene Journal, coming to us from Yorkshire, England. Good morning, Adrian, or afternoon to you.
Yes, afternoon in the UK and morning for you in Florida, I think, Debbie.
We are here today to talk about something extremely basic because we're always talking about graphene being a single atomic layer of carbon. So Adrian is going to explain to us the difference between atoms, bonds, molecules.
Good. So we've had a lot of questions on the YouTube channel, and I get a lot of questions on my email about atoms, bonds, molecules, things like Van der Waals forces, what's all that stuff about? And it gets really, really complicated when you try and sort of look it up on the web. So I'm going to take us through what atoms are, molecules are. If we can get on to Van der Waals forces, that's fine. We'll look at how that relates to graphene and two-dimensional materials, but we'll stick with graphene. Now I'm going to make some, I'm not going to dumb it down, but I'm going to simplify it. So you can go onto the web and get a lot more detail, but let's see how we go. So can I share my slides, Debbie? Great. So atoms and bonds. First of all, we need to know what atoms are made of. This does get more complicated at a layer below this, but for our purposes, we can just think of atoms as being made up of three things. So there are electrons, which you've probably heard of, and they have a negative charge. We've got protons, which have a positive charge, and neutrons, which have no charge. And that's basically it. Every single atom anywhere is made up of those three things, end of, for our purposes. With me so far, Debbie?
Yes, I am. This is my basic learning from school.
Right. Still, how the atoms are constructed, we have the protons and the neutrons clumped together in the middle, and that's called the nucleus. And then the electrons orbit round the outside in set channels, a little bit like a solar system you could think of, except in 3 dimensions rather than just a flat disk. Those orbiting electrons are called an electron cloud. A hydrogen atom on the left-hand side over here is just the simplest atom at all of everything. It's just got one proton in the middle in the nucleus and one orbiting electron. The electron's negative charge cancels out the positive charge on the proton. Because we're looking at graphene, I've put the carbon atom here, and you can see that's a little bit more complicated. We've got 6 protons in the nucleus with 6 neutrons, and then we've got 6 electrons that orbit around the outside. And again, 6 positive charges on the inside in the nucleus, 6 negative charges on the outside. They cancel each other out. And one of the bits of language we just need to get in our head is when we've got those electrons orbiting the nucleus, when it's just orbiting a single nucleus, it's called an atomic orbital. That's it.
Is that when it's not combined with anything else, right?
Right, yeah. Now, when we get to atoms do combine with other things, that's an important next step, because how they combine creates a bond. So all a bond is shared electrons. And if we use hydrogen as the simplest example of this, so the hydrogen molecule is H2, it's written normally as H subscript 2. And we've now got those 2 nuclei which come together, and they're the 2 protons. And then the 2 electrons get shared between the 2 protons, and they, instead of orbiting around a single center, they orbit around a double center. And this is now called a molecular orbital because we've now formed a molecule, and it's more stable like that than hydrogen would be as an atom by itself. So all a bond is shared electrons. Now, it gets a little bit more complicated, but if you think about the fact that those 2 protons there, they're both positively charged, aren't they? You can see that. And you realize, Debbie, that positive charges repel each other and opposites attract. So we've got a dynamic going on here. The 2 red protons are trying to push each other apart, and that those 2 orbiting electrons now are corralling both of those centers and trying to pull them together. So we've got this push and pull of repulsion and attraction forces in the molecule, and the net result of all that gives us a set distance between the 2 centers. And that's always the same for each type of pairing up of atoms into a molecule. And that's called the bond length. And bond lengths are always the same. They're the same combinations.
So that's when you show your molecular model, though the electrons where it's moving in the orbit is the straight part on your molecular model.
Yes.
It connects these together.
That's a very good thing to mention, Debbie. Yes, when we're drawing them on paper, or when you've seen me playing with my molecular models, then we've got the atoms are usually drawn or represented as spheres, and we've got lines or connecting rods between the two, and that's what atoms and bonds are in the molecules.
Okay.
In fact, let's just take a look at how they're represented. So again, looking at the hydrogen atom and the carbon atom, they're usually represented as hydrogen is usually represented either as the letter H and carbon letter C, or we've got a white sphere and a black sphere. Okay. And that tends to be how they're represented. And by the way, none of these drawings are to scale. They're just representations. And so how they're actually drawn, and you'll have seen me play with my molecules, that we've now got a little piece of graphene, and what we don't normally show on the graphene is around the edges, we've got hydrogen. So the edge of graphene sheets are terminated with hydrogens. There's a convention in scientists, Debbie, and chemists particularly, where we tend to leave off the hydrogens around the outside because it just gets in the way and makes it simpler. You'll see graphene represented as a hexagon of carbon, but we tend not to add the hydrogens on around the outside. Chemists know this, but sometimes other people don't, and it can lead to misunderstandings. And then here's just a single ring from graphene, single carbon ring, just shown side on, again with the hydrogens represented as white spheres. Is that all right for you?
Yes.
Let's see what else we can talk about. It gets a little bit more complicated because there are slightly different types of bonds, but we can play on themes here so you can understand what's going on. Where this is a sideways on view of graphene again, and you've seen me present this picture before, Debbie, but here are the normal, these are called covalent bonds when the electrons get shared between atoms. And that's what these lines are here. And in carbon, these bonds are some of the strongest in nature. But then you'll know that carbon normally forms 4 bonds, but when you represent it as chicken wire, you can only see 3 of the bonds. And so there's another type of molecular orbital that forms. A 4th bond projects up and below the plane of the ring, and it smears over the whole molecule. Not just the molecular orbital doesn't just cover one ring, it covers the entire molecule. So if there's a single molecule of graphene, which is, let's say, a meter long, then that molecular orbital covers the whole meter. We've got these continuous orbital going right across the whole structure. That allows electrons to move freely across the whole molecule, and that's what makes graphene so highly electrically conductive. And then there's a slightly different type of molecular orbital here between between pairs of carbon atoms, or 3 carbon atoms in this case, and they're the strongest in nature, and that's what gives graphene its strength. So we got slightly different types of bonds. I'm not going to dig too much down into the detail there, but does that help you understand how graphene, the bonds in graphene work, and the bonds with other elements work as well?
Yes, definitely. And it also explains to me how you can say that a large piece of like a large sheet of graphene, so to speak, is a single molecule. I could not put my head around that before, but it's because of those bonds.
Exactly, yes. Yeah. If you've got that constant repeating pattern, it doesn't matter whether it's sort of on a scale of a few nanometers like this, or we've seen people being able to make single crystal graphene at large scales now, centimeter scales. So this pattern just repeats and repeats and repeats. There is no limit to how big a molecule can be. And that's what makes it exciting for things like the space elevator, because now that we know we can make single molecules up to 0.5 meter long already, there's no reason why you can't stop and just make them a kilometer long, thousands of kilometers long, hundreds of thousands of kilometers long, one single molecule. Yeah.
I don't want to throw in anything that wasn't necessarily on topic, but does that explain how it differs from carbon nanotubes?
Right. Carbon nanotubes are graphene rolled up, and it's the same thing. So the bonds here, they just connect into a tube, and then you can just keep on extending out longer and longer. The problem with manufacturing carbon nanotubes is the longest anyone has ever made a single carbon nanotube is about 500 mil, which sounds long, 0.5 meter. But typically these things, industrial processes only make them in millimeters or fractions of millimeters long at the moment. Nobody's really cracked how to mass produce carbon nanotubes, whereas the industrial manufacturing of graphene is coming on in leaps and bounds. And
Yeah.
we're seeing graphene being made at kilometers long lengths, all right, on copper, and it's still polycrystalline. These molecules haven't totally connected up yet, but at speeds of up to 2 meters a minute.
All right. So when you were talking about the bonds, is that where van der Waals comes in to play?
Right, very good point.
Yeah.
Yes.
Okay.
Now, van der Waals forces, van der Waals bonds are what hold graphene layers together in graphite. And you see these little purple lines here.
Mm-hmm.
They're the van der Waals bonds. They are a slightly different type of bond. So it's more of an attractive, you could think of it like an attractive force. So it's not necessarily shared electrons here, because we've got electron cloud, then the positive nucleus, an electron cloud in between. But this is like a dynamic system. And what happens is that these electrons are whizzing around and randomly. And once every so often, if you can imagine from, let's just take these two atoms here.
Mm-hmm.
At some point, you'll find there'll be more electrons on this side and more electrons on that side. So the nucleus is exposed. So it's showing a little bit more positive charge here, and the electrons around here are showing a bit more of a negative charge. And what tends to happen is the electrons from one atom get attracted to the positive nucleus of the other one. And once that happens, then the electrons can't get back as easily because you've started to pull things together. There's still a repulsion, so you get this idea of push and pull. And this gives that van der Waals bond a bond length, just like we've talked about before. But it's not necessarily shared electrons this time. It's an attraction from the positive nucleus to the negative electron cloud of different molecules.
Wow. Okay.
And that gets repeated all the way through the molecule. And that's what holds graphite together in this layered regular structure. Okay. And that's what those purple bonds are there. And it's not just graphene. Van der Waals forces occur in all sorts of things. But does that sort of help you get your head around it?
Yeah, so that's what holds it together to make it graphite, and then to separate graphite out into the graphene sheets or the platelets, you've got to break those bonds.
Yeah. And the van der Waals bonds, they are quite weak, but there's lots of them. But that's why you can slide the layers over and exfoliate and pull it apart, because they're not as strong as other types of bonds. But you can imagine a very weak bond, but multiplied many times, will actually have a significant force. And that's what holds graphene layers together in graphite. We've got atoms, we've got bonds to form molecules. We've talked about shared electrons, and that gives us covalent bonds where the electrons are shared tightly around a pair of atoms. And then we've got where the electrons can get shared and smeared out across the whole molecule, which gives us molecular orbitals. And then we've also talked about van der Waals bonds, which are the electrostatic attraction between negative and positive charges in different molecules sticking stuff together. So hopefully that helps people understand what's going on.
Adrian, thank you so much for explaining this to everybody today. And if anybody